Hello everyone. I'm really glad that I've got this opportunity to discuss my work at this forum here today. Today I'll be discussing about signatures of cognition, especially what we can learn from the resting state EEG. Right. When it comes to our life experiences, from the moment that we are born, our experiences diverge. And similarly, because our experiences diverge, the signature of these experiences as reflected in our brain also diverge. However, in science, often we try to define the questions the other way around. We try to trigger things and see similarity between individuals. And here I'm not trying to say that it is not good to do this or we don't learn anything from this. However, the way we are approaching this problem is from the diversity angle. How can we quantify diversity or differences between individuals in the brain, right? So today in specific, I'm going to be talking about a metric called waveform complexity. And this is a way to interpret the EEG signal. And then I go on to talk about a few of the studies we've done where waveform complexity has been integral in interpreting either the stimulus experience or cognition in adults and even cognition in children. So what is complexity, right? Complexity can be thought of as an emergent property of a system. There are many systems, large entities, which are made up of smaller, simpler entities. And each of these simpler entities have certain properties. However, the larger entity itself demonstrates much more complex properties compared to the simpler individual entities. And to measure or quantify this larger entity is what can be loosely termed as complexity. However, when it comes to, algorithmically or practically defining this, complexity can be thought of, although it's different in certain ways, can be equivalent to entropy. And today I'll be interchangeably using these two terms. And entropy and complexity are essentially measures of diversity, unpredictability, or uncertainty in patterns produced by the system. When it comes to here, there are three examples of systems, right? Where, for instance, in a colony of ants, you can see the individual ants themselves don't demonstrate the same behavior that the colony demonstrates. Same with a school of fish or a flock of birds, and in our particular case, behavior from the functioning of 10 to the power of 15 individual neurons in the brain. And EEG essentially is a higher order emergent signal which comes from the brain. And in the space itself, entropy of EEG is calculated and in many different ways, and I'll be talking about three different ways today. And entropy of EEG can be thought of as how repeatable or how regular the EEG signal is. For instance, one of the popular measures is sample entropy. So in sample entropy, what is done is the whole EEG signal is taken and it's broken into small segments, typically between very few milliseconds to up to 75 milliseconds. And the vector distance between each of these segments is estimated. And from there, we kind of infer what the entropy of the signal is or how repeatable the signal is. Spectral entropy, on the other hand, as the name suggests, is in the frequency domain, right? You transform the signal into the frequency domain, take a window of interest, frequency window of interest, and calculate the entropy for that particular segment. And number Z complexity, right? And this is it's widely used in fact in audio compression. So here coarse graining is done where the signal is taken, analog signal is taken and made into zeros and ones based on a thresholding. And different distinct patterns are measured. So the more patterns that we can count, the more random the signal is. And fewer the patterns, the more regular or repeatable the signal is. And all these measures of entropy, which are being used in EEG today, make implicit assumptions either about the length of the signal or other such features. However, a priori, we really don't know what aspect of the EEG signal is that we are looking for. So this was our motivation to actually create and think about this metric called as waveform complexity. So here what is done is the waveform, the EEG waveform is taken, and 100 segments, 100 or some such number of segments is taken, represented here in red across the signal. And the correlation between each of these segments is measured. And 1 minus correlation essentially gives you the distance between these segments. And median value of that, which is shown here in the cumulative histogram, each of these gray lines represents a separate electrode, and the black line here shows the mean of these values. And the median value of this distance essentially gives you a measure of complexity. And complexity, as we define, ranges from 0 to 100. So this measure is different from other entropy measures which I just discussed now, because the time scales are a little longer. We look at 500 to 750 milliseconds, which represent time scales of human perception. And another thing, because we're using correlation instead of distance to measure similarity between waveforms, the shape of the waveform becomes important to this measure, right? And it's independent of the amplitude. An analogy which can help us think about this is, if I'm a person who's looking at a text and I don't know anything about human language, then whether to interpret it at the level of a single letter or at the level of single word completely changes the way I look at the signal itself. And that's what we're trying to achieve using this waveform complexity. I'll move into some of the studies which we've done where complexity is integral to interpreting the stimulus environment. So this is data from a study done in Tamil Nadu in India. Tamil Nadu is a southern state. It's quite industrialized. We've got recordings, EEG recordings from 402 participants. And here the participants came from a diverse range of socioeconomic strata, starting from people earning a few dollars per day to people earning up to $50 per day, and having a various wide range of education, wide travel patterns. So we try to capture the essence of this socioeconomic diversity. And what we found is that complexity scales really well with stimulus consumption. So the more complex your environment is, the complexity of your EEG signal is higher. And here, this by stimulus factor, essentially it is the principal component formed from education, years of education, travel patterns, fuel consumption, phone usage, and electricity consumption. When we try to break it down further, we found that complexity actually draws strong parallels with level of education. So as you can imagine, as the years of education goes up, the complexity of the environment the user goes through also increases. And that seems to be captured well by this metric called waveform complexity in the EEG itself. And we can see the same sort of linear relationship between complexity and travel patterns in these individuals. So complexity reflects, waveform complexity essentially reflects the complexity of the environment the participant is going through. And this study, I want to reiterate that all the studies I'm showing today, the recordings were done at resting state EEG with participants closing their eyes and recording for just 3 to 4 minutes from each individual. So then we went on to see, okay, complexity has a lot of parallels with the stimulus environment, but does complexity say something about cognition itself? So in 28 adults, we gave them 5 questions, Raven's progressive matrix. So they are given questions like this pattern shown here, and the user needs to say which pattern comes next, and they need to pick from a choice, 4 choices given to them. There were 5 such questions given to every user. The EEG recording was done before the test itself. So it is a resting state EEG, and it's not by the users giving the test. And what we noticed was a surprisingly strong correlation between the score in this pattern task and the waveform complexity. And we can see that the correlation shown here is as high as 0.61. And here the color in fact represents the change in this correlation once this data, one single data point is removed. And as you can see that this one individual with the complexity over 80 is skewing this a bit. And once we remove this outlier, in fact, the waveform complexity correlation goes up to as high as 0.71. And this result, of course, hints at a relationship between complexity metric and cognition as measured by this pattern completion test. So, like I went into some of the other measures of entropy which are related to complexity, we wanted to see how related they are to complexity. And you can see that all three measures, spectral entropy, sample entropy, and Lempel entropy, have a high correlation with the waveform complexity itself, ranging from anywhere between 0.71 to 0.82. However, when we look at the correlation with the outcome metric, waveform complexity does significantly better. One reason which might attribute to this is that the variance which we had in the waveform complexity was higher compared to the spectral entropy and sample entropy. So we got a wide range of values in the 28 participants from 51 to 83. And that equates to a coefficient of variance of around 13%, 13.7%. So then we looked at whether if any specific electrode had a better correlation than all of them put together. That was not the case. However, the frontal electrodes did show a tendency to have a higher correlation compared to, say, the occipital lobe electrode. And we also looked at variance across electrodes in individuals. And this ranged from as low as 2.7% to as high as 17%. And this variance was inversely related to the score in the random test. So which really goes to show that having lower variance is probably correlates better with more stable complexity. Right? And with this, I'll be moving on to how cognition, whether we can measure cognition in children using measures such as waveform complexity. Before that, I just want to put out one caveat, which is that the test that we gave had only 5 questions, and it's a small sample size of just 28, and therefore we believe that this must be further validated. However, this suggests that waveform complexity does reflect what your stillness complexity is, in particular cognitive outcomes. Right? So this here we are looking at cognitive outcomes in children, and this study is done with Vikram Patel's group in India. And here we did the study in the northern state of India of Haryana. And we looked at children, 3-year-old children, 33 to 36-month-old. 70 children, for 70 children, we did the Bailey's test. The Bailey's test can be thought of as a scale which measures cognitive, language, and motor skills in children, in very young children. So first, the resting state EEG was recorded in all these children. After the resting state EEG was recorded, the children went through the Bailey's test. And then the EEGs were analyzed for a series of metrics. And today in specific, I've been talking about the single metric called waveform complexity, but we also kind of analyze temporal metrics, which captures the essence of the amplitude of the signal, then synchrony metrics, which captures the shape of the signal, and spectral metrics, which are most popularly estimated, which is a power spectrum of the signal and related to the alpha peak, right? And eventually the goal for this study is to predict developmental cognition in children from these metrics. Right. And what we can see is this histogram on the left shows the cognitive scores across 70 children. The bars in red show children whose score is less than 65, and these are the children who probably need intervention. And this is children in the middle, and these are children with higher scores. And this plot over here is just a simple plot of histogram of complexity between the red group and the green group. And we can see that complexity has the ability to differentiate these two groups to a significant effect, and children with the higher scores in the Bailey test have cognitive complexity slightly shifted to the right. Further, we looked at all the 14 metrics which I just shared, and we looked at the correlations between these metrics and clustered these metrics, because as we know, EEGs are highly correlated to each other, and so are many of these metrics. They are quite correlated to each other. And as we can see, that waveform complexity provides a different view of the signal, and it sort of stands out among the spectral, temporal, and synchrony measures.
Okay,
we looked at the cognitive score in children, and we found that 7 of these metrics which we looked at were significantly correlated with the outcome metric. Out of these 7, we selected 3 based on how closely related they are to each other. And by selecting these 3 metrics, A as D, it represents the standard deviation of the amplitude, waveform complexity, and beta. Beta just stands for the power spectrum in the beta range. We got a very good AUC and good predictability with a simple logistic regression model. And the scores from the model were inversely correlated with the actual cognitive score in children, with a correlation of minus 0.458. And complexity does seem to be quite reflective of cognitive ability in children, although we needed to include a few more of these other features to bring out the best. So in conclusion, I want to say that waveform complexity itself reflects lifetime stimulus complexity, and which in turn is predictive of the cognitive outcomes. Though they may be specific to particular types of cognition, which we've gone through today. And before I conclude, I just want to thank all the people who've been involved in this project. One is the REACH team, with whom we've been working on the cognitive development in children. And this team is driven by Vikram Patel, and we work closely with Debarati and Supriya, who's been a part of the whole process of thinking through how we can predict the BSID score. And Kamal on the field has been integral in collecting data from Haryana, speaking the local language, and getting children to get ready to wear this device and record EEGs. And of course, our Sapien labs team, and most of this work has been conceptualized between me and Dhanya, and Narayan has been integral in the entropy part of the measures which I shared in the beginning. And Satish was critical in our Tamil Nadu project, where he drove the whole data collection from the field. And with that, I conclude my talk. Thank you.